Hello and welcome to our video. We are Bug Busters Team 106. So just before we begin, I'm going to give you a quick demo of our program. So /gen village, and we'll just do size 50. So right now it's scanning around for some good plots, and it's found some good plots. It's placing those down, doing some terraforming. And then once it's fully terraformed, it starts building houses on it and a wall around the village. I'll just go inside one of these houses while the rest load, just to show you. So it's fully decorated inside. We have rooms of different themes, different furnitures, done by recursion. And once all the houses are down, our pathfinding algorithm starts, and it will find the shortest path between each of these buildings. As you can see here, they're all connected with these gravel paths, so each building's connected to another. So as you can see, if we follow this along, connects to this building, got another connection here to this building, and it does this by finding the shortest possible path.
Hey, my name is Nanintab, and I'm the one who worked on Task A for this generation, and my student ID is S4055228. So what does Task A do? The process starts by scanning either the player's location or the location that is given to define a village boundary by the given village size. The program then searches the height map for valid plots and then stores each valid plots. And basically each plot is validated by their max slope delta, whether it's inside the village, their water percent, and also if they intersect with other plots. And once the plots are chosen, as you can see here, terraforming begins. And first, it takes out all the trees from inside the village boundary and a bit expanded from the village boundary, depending on the plot border. And then afterwards, it starts building the slope using the apply vertical column function. And slopes are built depending on whether the terrain is higher than the plot or lower. For example, if it's lower, we'll build down, and if it's like higher, we'll build up. And basically next we have the place wall and function, and it places a wall around the village on the boundary, and then basically as it uh, builds, like it scans and checks for the highest y coordinate, just so we can make sure like players cannot parkour from here, and also at the same time places the glass block so spiders cannot cross over. And then afterwards, we have the find waypoints problem. And for example, for these groups, these plots, it will group them starting from the one closest to the top left corner into trios, and the leftover plots will be made into duos or singles. And then it calculates the central point and validates them against existing plots. And these waypoints will be later guide pathfinding in task C. For ADTs, I did use several ADTs, for example, vector and then coordinate and coordinate to the block type height map and chunk from FCPP. But a few of my custom ADTs were my batch plot structures and my reg block structure and my village plot class and trio structure. And for here, I'll show you my batch plot and reg block. And basically, I chose these simple structures with clear fields like over inheritance to avoid like complexity, and mainly because like performance matter for like large worlds too. So this just made it much more clearer and much more approachable and easier. And it just like helps me like get away from like doing more repetitive like coordinate maths. And basically this approach keeps data and behavior like separate and ensures that like each structure has a single clear responsibility. And for testing and verification, I verified my test through a dedicated test mode. And once that test mode is run, I can choose 5 different components to whether test my find plots, terraform, wall tests, or waypoints, and all just to like test all of them at the same time. And basically for plot and waypoint tests, I print out variables and I'll show them right here. And basically it prints out the variable datas, and that just makes it easier to check. And the same goes for waypoints too. But for Terraform and wall tests, I use screenshots for the expected output. As you can see, like the wall or Terraform, they both give a lot of coordinate data, and it's really hard to check. And then afterwards, I can just like run these separately in my test mode, and all of, for example, find plots and waypoint is also made sure that like there isn't any like randomness, especially even for the find entrance function too. And basically afterwards, my like each of them can be run like individually, and which I'll show here. So I'll run /gen village and then test mode. And let's just say village size is 50. So I'll choose task A, and then I'll choose 5 just to show all the components at the same time. Basically starts clearing, terraforming, and then since plot border is 10, there can only be like one plot possible. But this finishes the entire task A. And task A uses defensive programming, especially in a wall for like clamping Y, which is from the clamp Y function. It's just basically ensures that like I stay within the wall bounds. And for structured programming, it uses like helper functions that has like one return statement. And as you can see, it's just only single return statements and no breaks or continuous statements. And I define like the constant globals in the config file. And for programming by contract, for example, each function has a precondition and a post condition. So let's say for clear trees, the precondition is that it needs MC, the village plot class, and the plot border. And then the post condition is that using those, it will replace all tree blocks with air blocks within the village boundary and a bit away from it, depending on the plot border. And this is what it does. And in conclusion, task A automatically generates a build-ready village by locating valid plots, terraforming, building walls, and placing central waypoints. And through strong ADTs, systematic testing, and disciplined defensive and contractual like design, I believe my implementation is robust, testable, and forms a solid foundation for the later stages of the project. Thank you for watching.
Hi, I'm Callum French. I worked on task B, which is building the actual house. So I get the plots from task A and build a house on it. So I'll just give you a quick demonstration. So this is me hard coding a plot just so I can show you easier. So it wants me to enter the number of houses we want. Just one house is fine. And we'll make the plot 20 by 20. So as you can see, it builds a house right at the player's location. You can go in, it randomly subdivides the rooms up, just, having the minimum 4x4 to 8x8. And then it decorates them. So as you can see here is the living rooms and bookshelves, bedroom with a bed, bathroom with a nice bath, kitchen with some sinks and stoves. Come here, here's a bathroom with a toilet. The height is also randomly generated. So it'll be random each time it's ran. Some appropriate data structures that I've used is I created a custom class for the room info, just because with the subdividing, creating a lot of rooms. So we've got it here where it holds every corner of the room. If we can, split the room again, the length and width of it, just because a lot of these I'm reusing again and again for each room. So it just makes sense to create a class for it to abstract, all these corner calculations, just validate the coordinates. And yeah, because everything's related, it's easy to just put it into this class. I've done a lot of testing with this, so I will just show you how my testing works. So if I do /gen village space / test mode, a list will come down saying what task do I want to do. I'm task B, so I want to do task B tasks. And then from here, I can choose which thing to test. So we will do a subdivision along the largest axis, and I'll say, what size do I want? I'll say 17. And then it'll place one in front of me. So I've got the roof off just so it's easy to see. As you can see, it splits it pretty evenly across down here, down the direct middle. And then here, because there's a door here, we don't want a wall right in front of the door. So what I've made it do is just shift it one to the right, which works very well, proves that you know, you can always access the house. Furthermore, there's always a door one block off from the wall, which also allows access into every room through a certain route. And yeah, as I just showed before, we have lots of other options, which I have shown in my testing. Cool, and that's all the functionality and my testing for it. So I want to show some of my defensive programming. So as you can see here, if the user, I'm task B, there's options 1 to 5. So what if the user wants to test number 9, which doesn't exist? It gives them a invalid number error, then asks them to enter it again. So got a nice error message, re-prompting so the user knows what they've done wrong, and it'll keep looping through that until they enter a valid number, which here is 1, 2, 3, 4, 5. Another thing I've done well is structured programming. So I'll use this function as example. There's one clear entrance, one clear exit, and then inside it we are calling all of our other functions. Just make it nice and clean, so we don't have one function that's like 200 lines long. So calling the build floor, build wall, and build door. So as you can see here, build floor, build wall, and so on. So it's just all nice and nice and together. It's easy to see what's going on. And finally, as you've already seen, we've got a lot of programming by contract. So here we go. As you can see in my room subdivisions function, we've got our contract. So preconditions are all corners and entrances are valid coordinates. The wall height is valid, which is greater or equal to 0. The room dimensions are greater or equal to a 4x4, which is the minimum room. And then the post conditions from that are it subdivides the room into 4x4 or 8x8 rooms, somewhere in between. So for every function we have a contract, and just what it does, just make it nice and clean. And that is all. Thank you for your time.
Hello, my name is Nyome. Thanks for having me today. I am doing testing for this group project, and testing is about pathfinding between houses and waypoints. So I made my own queue in TestCQ to have the breakfast search algorithm. It has simple functions like queue initiate, queue push, queue pop, and queue empty. These are helpful functions. A queue was in fast and fast out order, which is perfect for BFS and explore the grid in the right orders and always find the shortest path. So here I created some stress to have my breakfast search algorithm. I have 4 stress here. Number 1 is I2. This is just for 2D search. It's not included Y, the height. So in 2D search, I name it I2, and then like 3D, which is included Y, I name it I3, and then we have B box, the stress that define the maximum X and Z value, which is the rectangle in the map. It's like the house area and then plot areas, and then last we have field. In field we have the initial point, and then like we have parent nodes and we have visited. So it's like we have the initial point and then we have the target, and then when we reach the target we trace back to the initial point. So this is like where I store all my data for my algorithm. Yes, this is the function that finds the center point, the half of the village. First is average all the house entrance coordinates to get rough middle. Then it checks the nearby area around the average of nine square blocks, 9 blocks. So to find a better position, in case that was inside the house or inside under the building. So, and then it used the same distance, Manhattan distance as the score to get the to make that is the most efficient point for every houses. Finally, when it's set, X and Z value get the Y value and then set the point and then return the value to the function to do the hap to find the to the preferred search algorithm. So this part is where I connect all the doors to the center part. So what I do is like I take the value of the doors, the entrance, and then I calculate the center hub. And then from the center hub, I run the preferred search algorithm, and then it's reached the door. When it's reached to the door, it trace back the parent node and then get to the center point, and then we lay the path. So this is the main part to get to lay the part to the from the door to the center. And this function is just a helper function that I use when I build the part on the water. Like sometimes I have to cross the water to connect the house to the center hub. Like in that case, when I have to pass on the water, the underneath the path, the underneath part, the blocks has to attach to the solid ground. So like in case the bridge is only on the air or only on the water, and then the underneath the bridge, the structure has to, I make sure the structure touch the solid ground. So like this kind of, you can see here, air, like flowing water, still water, lava, and still lava. This kind of thing are not stable. So I make sure that it is like visually appealing, makes sense. The bridge have to go to the solid ground.